All right, so today we're going to introduce molar mass. That's a concept you're going to have to use throughout stoichiometry, so it's a really good place to start. So, we use different values to measure things. When we get a dozen eggs, we have 12. When we order a baker's dozen of like cupcakes or donuts or something like that, that's 13. So a mole in chemistry is just another way to measure a very large quantity of something. And specifically, what we're talking about in terms of what it's going to measure is going to be atoms. So a mole is a way to measure the amount of a substance, particularly really, really small things, such as atoms, particles, molecules, those types of things. So we have something called Avogadro's number, which is 6.022 times 10 to the 23rd. That's the number of particles or atoms or molecules in 1 mole of anything. So it doesn't matter what the substance is, if it's an element or it's a compound, if you have 1 mole of it, you will always have 6.022 times 10 to the 23rd atoms or particles of it. So if you have 1 mole of oxygen gas, O2, you have 6.022 times 10 to the 23rd atoms of oxygen gas. If you have 1 mole of water, you have 6.022 times 10 to the 23rd atoms of water. The reason why we refer to a mole is because 6.022 times 10 to the 23rd, that means it's like 6 billion or trillion billion atoms. It's not something you can really count. So we want to have some way to quantify that amount. So the mole is a great way. Now, a mole is not always the same amount. So let's look at this, for instance. You have here in the picture a dozen eggs and you have a dozen bowling balls. Okay, the amount of both of them are the exact same. You have 12 eggs, you have 12 bowling balls. We can count them, you'll see they're the exact same. But what might be different about them? Do they have the same mass? Would they weigh the same? No. A dozen eggs would obviously weigh a lot less than a dozen bowling balls because bowling balls usually range somewhere like 5 to 10 pounds a piece. An egg is not even a pound. So you're having a significant difference in the mass or the weight. So even though we have the same amount of them, our mass or weight are different. And that's the exact same thing with a mole or with mass. Your mole is going to tell you the same number of atoms of a substance. Like on that previous example, we have 6.022 times 10 to the 23rd atoms of oxygen and 6.022 times 10 to the 23rd atoms of water. But the masses of the two are going to be different. So that's where we come to something called molar mass. So molar mass is the mass of 1 mole of a substance, and every substance has its own unique molar mass. Molar mass is going to be measured in grams per mole. It's kind of like miles per hour, same kind of idea. Grams per mole, which is G/MOL. Moles are kind of weird because there's not really a great abbreviation for them, so we abbreviate them MOL. And then grams is always abbreviated with a G. So 1 mole of a substance will have a set molar mass, and every substance has its own unique molar mass. So you'll probably want your periodic table handy. I'll kind of give you a little snapshot of the periodic table on the next slides, but you'll want your periodic table handy for sure. So let's look at a compound, lithium fluoride. LiF. It's made up of Li is lithium and F is fluorine. So to figure out what the molar mass of lithium fluoride is, we are going to take into account what their masses on the periodic table are. So lithium's mass on the periodic table is 6.94 grams. Fluorine's mass on the periodic table is 19.00 grams. So lithium has a mass of 6.94. Fluorine has a mass of 19.00. So to get the total molar mass of lithium fluoride, we are simply going to add them together. And when we add them together, we get 25.94 grams per mole. Or we say 25.94 grams is the molar mass of lithium fluoride, or 1 mole of lithium fluoride equals 25.94 grams. So 1 mole of lithium fluoride equals 25.94 grams. So that's how we're going to do it. We're going to be taking the masses of each individual element and adding them together to get a total molar mass for a compound. So let's look at a couple more. So N2. N2 is nitrogen gas. Keep in mind, nitrogen is one of those 7 diatomic molecules. So when it's by itself, it's always written with a subscript of 2 because it is a diatomic. So nitrogen's mass on the periodic table is 14.01 grams. While in N2, there are 2 atoms of nitrogen. So we're going to take that 14.01 grams and multiply it by the 2 nitrogens that we have. So that's going to give us a molar mass of 28.02 grams per mole. So that means, oops, that should say 28.02 grams is the molar mass of nitrogen. I typo right there, excuse me. Or 1 mole of nitrogen gas equals 28.02 grams of nitrogen gas. So when we find the molar mass, if there's a subscript, that's going to tell you how many atoms of that element there are. So you're going to multiply that subscript by the mass of that element. So let's look at one that's in a compound with more than one different element. So calcium hydroxide, CaOH2. So calcium hydroxide is made up of 3 elements: calcium, oxygen, and hydrogen. So calcium has a molar mass of 40.08 grams. Oxygen has a mass of 16.00 grams. And hydrogen has a mass of 1.01 grams. But in this case, we have a subscript, we have parentheses, so we have a lot of different things we have to look at here. So same kind of idea as when we went through and balanced equations to tell what we have. So Ca, there's no subscript next to Ca, so that means there's just one Ca in calcium hydroxide. So its mass is going to be 40.08 grams. But you'll notice there's this subscript of 2 on the outside of hydroxide. That 2 is going to apply to everything on the inside. We are going to multiply. So that means there's 2 times the 1 oxygen on the inside. So we have 2 oxygens times oxygen's mass of 16 grams. Gives oxygen a contribution to calcium hydroxide of 32 grams. Then this 2 is also going to apply to your hydrogen. So you have 2 times the 1 hydrogen in the compound. So you're going to have 2 times hydrogen's mass of 1.01 grams to give hydrogen a contribution of 2.02 grams. You're going to go through this and do it for every element that's in that compound. And then once you're done, you're just going to add them all together. So you end up taking 40.08 plus 32.00 plus 2.02 to get a total of 74.10 grams. So 74.10 grams is the molar mass of calcium hydroxide, or you can say 1 mole of calcium hydroxide equals 74.10 grams. You do want to make sure that you are using the masses on the periodic table correctly. Don't want to make up your own masses or round masses unnecessarily. So I'm going to have you try a few. Carbon dioxide, what is the molar mass of carbon dioxide? Then I want you to try Li2Cr2O7. And then I want you to try ammonium phosphate, NH4 in parentheses with a 3 on the outside, and then a PO4. Go ahead and try those 3 and see what you get. And then let's take a look and see how close you are. So carbon dioxide, you should have gotten 44.01 grams. Carbon is 12.01 grams, and then oxygen is 16 grams times 2. So Li2Cr2O7 should have gotten 229.88 grams. And then for your ammonium phosphate, that NH4,3PO4, you should have gotten 149.12 grams. So let's look at that ammonium phosphate. What happened to the ammonium phosphate? Where did we come up with that? If you struggled on that one, try and follow along and see what I did. So you have the NH4 here in parentheses with a 3 on the outside and then PO4. Well, that 3 is going to apply to both the hydrogen and the nitrogen. And keep in mind, it is a multiplication. We are multiplying on both of those. So that 3 is going to multiply by the 1 nitrogen in there. And that's going to mean we have 3 nitrogens. That 3 is also going to multiply by the 4 hydrogens we have in the compound. So that's going to give us a total of 12 hydrogens. Then there is no subscript next to the phosphorus, so that means there is just 1 phosphorus. And then there's a 4 next to the O, so that is 4 oxygens. So it's very much like when we're counting to see how many of each element there are when we were balancing equations. The same idea is going to apply here. Then you're going to multiply each of these numbers, the 3, 12, 1, and 4, by each of the corresponding masses on the periodic table. Add them all together, and you should end up with that 149.12 grams per mole. So when you're doing molar masses, I want you to round to at least 2 digits past the decimal. That's what your periodic table shows, so I want you to continue with that. And we're going to keep working on this, and this is going to lead us into what we're going to be doing in the rest of this unit with stoichiometry. We're going to use these molar masses as conversion factors for all of the problems we're going to be doing throughout this unit.